Alright, so guys, thank you for getting the books out so you can write your notes. Tommy, you can do that afterwards. Love it? Love your work? Alright. Let's edit the hell out of this, shall we? Alright, year 11. I need you to be focused. You can use your screens if you're on topic, but otherwise kill them so you can stay on topic with me. But today, this is our last tiny bit of theory to cover topic 1. And that means on Friday, hopefully, we have enough time to move on to our second topic, which I'm actually slightly excited about because it looks like it's going to be fun. But guys and girls, to finish it off, we're going to talk about data types. And I've got a challenge for you without you clicking through the slideshow. Somewhere in your book, potentially the back, I would like you to list all the different variable data types that you can think of. Go. Alright, boys and girls, can you join me just for a bit? I was up for you guys, so let's have a look. Most people got the bare basics, integer, straight bang on. So what's an integer, Sam?
Number.
Fantastic. A lot of people got strings. Tommy? What's a string?
Like characters.
Fantastic, that's really well done. A lot of people got floats as well. Adrian, what's a float? Pick it on you. Pass? Ben?
Decimal number.
Decimal or fractional numbers, very nice. We had another good old friend, the Booleans. Harry, a Boolean. Absolutely spot on, true or false. There was a few people that put date time. Absolutely love your work. Taryn, what's a date time?
Yesterday.
It's a date and a time. Yeah, exactly right. Did anybody else have any more?
I had definition in there, but I'm not sure.
Doesn't count as a data type, but that's very nice. I like that one. Taryn? Ooh, okay, a list. What's a list?
It's a collection of strings.
Or
Characters.
Or
Integers.
excellent. Love it. Yep. I actually like you brought that one up
Characters as well.
because we're actually okay, yep, sorry. I'm trying to talk and you characters. You're excited, I know. Alright, we're going to talk about lists a fair amount today, guys and gals, and I'm going to reintroduce lists and we're going to show you different extensions, how far they go. But what I quickly want to talk about today, we are not going to do much Python until the end of the lesson. So a fair chunk of theory for you all. What I quickly want to do is go through these data types that we've got listed here. And I want to talk A, what do they do? B, what's their limitations? And C, when would you use it? Does that make sense so far, everybody? Okay, so we've got the basics down pat. What's a data type? Well, anytime we store data, we have to choose a type. Who can tell me, why is there such a thing as data types? Why can't I just smack any old thing into my program? Why do I need Python to know about integers and strings? And what do you reckon, Hayden?
You don't know whether or not a byte is represented with a number or a letter.
I love that. That was actually the example I was thinking of. So boys and girls, imagine I had this stored in RAM. Just 8 ones and zeros floating around. 8 ones and zeros, what do you call that? Hayden's already said it. It's 1 byte. 8 bits is a byte. But boys and girls, you look at that. Who can tell me what that represents as a decimal value? 64 and 8. So it could be 72, couldn't it? Okay? That's if, what kind of data type? If I look down this list here, what data type would this byte become 72? It's an integer. Bang on. I'm going to put int in brackets on the front. Now, what if it's not an integer? I'm going to write the exact same binary, and you guys can write this example down if you'd like, if it helps. What if it's a character?
So it would be.
See if anyone can remember.
Let me bring up my table.
Yeah, go for the table. Yep.
It's not
Capital H.
table.
Nice. So this could be a capital H, boys and girls. What if, yes, I'm getting more and more annoying. Bear with me. What if it's a Boolean?
It would be false, true, false, false, true, false, false, false.
You'd think that, it's actually just true.
Wow. Why?
Because the way Booleans work, and I'll get to this, is they use 1 byte of data. All zeros represents false, anything else is true.
If there's any true in there, it's true.
Yeah. If there's any true, it's true.
It's just a massive or statement.
Exactly right. So this is why we have data types, boys and girls, because You can have this giant string of binary bytes, whatever. You need to know, well, how do I interpret that? Do I just interpret it as a decimal number? Do I interpret it as an ASCII character? What about true and false? Now, notice I didn't touch on float or date time or technically string. I don't want to do that just yet. We'll get there in year 12. It goes pretty insane. So boys and girls, these are the 6 that I want you to take away, okay? I want you to walk away going, character, string, integer, boolean, float, date time. Everyone cool with that? These are called your primitive or standard data types. Does anyone know why they're called primitives? Because they are basic. They are the simplest data that you can have in a programming language. So if I need a single letter, then what data type will I use? Bingo. If I need to store the value of pi, 3.14, what would I use, Dobby?
Oh, float.
Float, absolutely spot on. If I need to store Will's birthday, Will, what am I going to use?
Date time.
You're best off using the date time. However, what if I want to store someone's gender? Oh, string's a good one.
You can do character.
I could do a character. Technically not Boolean anymore. We're going to be fluid. Can't have just one or two. Whether you believe it or not, you need to support the world as we move forward. So strings, characters, even integers could work, couldn't they?
Yeah.
You could just make every number represent, just like ASCII characters, 0 represents one of them, 1 represents another gender, 2 represents another gender, etc., etc., etc. You couldn't really use date time for that. I mean, if you really wanted to, you probably could. But moving along with our lives. Let's go through some of these things, boys and girls. So, let's say, these are your headings, by the way. I'd like you to summarise my notes. I've tried to keep them pretty simple so we can blast through today's lesson. But our first data type, the character. It obviously represents a single letter, number, or special character, really. Does anyone know what I mean when I say alphanumeric? Taryn. He beat you by 0.1 of a second. Taryn.
An alphanumeric keypad is like the 1 through 9, and then I just know because I used to have a Nokia, and it had like the interchangeable with letters, but I'm not. I guess it's just like alphanumeric is both letters and numbers.
Absolutely spot on. Alphanumeric is letters and numbers. So if you need to store just an alphanumeric letter, you would use a character. Okay, simple as that. But guys and gals, we've actually got 2 types of characters to absolutely screw with your head. The first one that we've been using already is called an ASCII character. Okay, you guys are remembering this table that we used in the last lesson that we did? This is known as the ASCII table, okay? These are your ASCII characters. Can anyone tell me what's the biggest issue with ASCII, that ASCII table when you look at it? What is it?
You can only use English.
You can only use English. If you've got Japanese, Korean, anything on top, even French or German letters, you're screwed. ASCII only supports Latin, if you want to get technical. Why do I say Latin, Adrian?
Why?
Yeah.
We use the same alphabet.
We use the same as the Latin alphabet. A, B, C, D, E, F is Latin.
So do a lot of languages. So you could hypothetically have Spanish, but are the accents stored in ASCII?
No.
Yeah.
Not many. There's a few, but not many. So guys and gals, have a look at this. An ASCII character is a single byte. That means we only have a maximum of 256 characters, and that is it. We run out of binary at that point. So, obviously, computer scientists said, this is a dumb idea. Let's invent something new. Let's do something that is future-proof, something that supports more than just English and some random-ass numbers and things. So they invented Unicode. Can anyone tell me what Unicode might stand for? It's a portmanteau of 2 words.
Universal code.
Universal code.
We didn't like universal code.
It's literally future-proof, guys and gals. As of me writing this slideshow, in Unicode, there's 149,813 characters in Unicode. That includes hundreds of languages around the world. It includes English, of course, as well. It includes numbers. It even includes emojis. So if your program supports Unicode, you can support every language around the world and Unicode characters. If you want to go have a look at it, type in Unicode table and have a little bit of a scroll and get lost. Yep.
Every Unicode character is on your keyboard. If you press Alt and then type in the code, you'll get it. Like 233, you use the rectangle.
Do you know what? You're actually typing in ASCII characters when you do that. That's the 233rd. ASCII character. So if you hold Alt and press 65, you should get a capital A. But guys and gals, the Unicode table is just ridiculous. There's no way you would ever remember it, and you'd never expect it to. But the really cool thing about Unicode is it's backwards compatible. So that means the first 256 characters in Unicode are the exact same as ASCII. So if I use Unicode and I get a 65, it's a capital A. If I use Unicode and I get a 97, it's a little a. So it's backwards and forwards compatible. That's pretty cool. So guys and gals, I'm going to leave it there for a second. Write down any notes you need to do. Have a look at those tables. Okay, boys and girls, come back. The next thing is to quickly talk about strings. So you guys have used strings since day one. When you went into Python and you typed print hello world in brackets, you literally printed a string to the screen, which was hello world. Okay? A string is literally a list of characters, and that's all it is. The really cool thing about strings is basically your programming language will try and store characters for you. It could be ASCII or Unicode, doesn't matter. Python by default, by the way, will use Unicode characters for its strings. So yes, you can use emojis if you wanted to. Some people did in their Python, not Python, Hangman games. It was fantastic. However, I've got a couple of questions for you. And it's already on the board, but what's the best data type to store a phone number? Why is it a string? It can have spaces, that's a good one, but it's not the main reason. Tarek?
Because it's several like different. You want it registered as these different numbers instead of just one really big number in like the billions.
You're getting warm, but that's not the main reason. What do you reckon, Brody? You can't do math on a string, and we don't want to do math on phone numbers, but still not the reason. The main reason. Bingo! Guys, have a look at this random phone number I typed in. It's got a 0 on the front. If you put that in an integer, Python would actually remove the 0 because like zeros on the front of numbers aren't important, are they? But if my phone number went from 04 to just 401, that destroys the number, doesn't it? Doesn't work anymore.
Like the plus 61 thing?
That's like international style things. Yeah. But like if it removes the 0 off the front, the phone number's ruined. So we must use strings. The spaces and the fact that we don't want maths is just a cherry on top, I would say. Okay, so when you store your words, let's say you store hello word there, Al, you're getting a bit distracted, I feel. Every single letter is basically given an index, because remember it's in a list, so hello world would become HELLO space WORLD. Okay? Stupidly enough, even the spaces need their own character. Why is that, Val? Why do you reckon?
It's just how it does it.
It's just how it's done? It's just how we do it? Why do we have to have...
It's like an invisible character.
Sort of.
Is it because it's on the ASCII table, so it's coded in there?
Yeah, it's coded in. It's got its own ASCII value. Exactly. We still need to print the space, don't we?
Yeah.
If we didn't know about the space, it would just be two words jammed together. We need a character for the space. Fun fact for you, there's actually 12 characters there. It stops at 10. Why am I saying 12? We reckon, hey?
It starts at 0 and there's an AND character.
Well, bang, got it in 1. Yes, it starts at 0, so that means there's actually 11 on the board there, isn't there?
Yeah.
There's actually one over here that's hidden. And this is called your null character, which tells Python, I'm finished. It's the end. Okay? So how many bytes of data? If I was storing that, how many bytes of data would I need to just store hello world? Including the invisible one? 12. Because every character is at least 1 byte. So we need 12 bytes for that one. Okay. So guys, I want to move on to the next one because strings are fairly straightforward and I feel like most people are probably being taught how to suck eggs. This is where the fun begins. Integers. Dobby, what's an integer? Ooh, thank you for adding that extra word. A whole number. So if I said something equals 5.1, what would happen to the 0.1, do you think, if it was an integer? Gone. It would just be 5, and that is it. Okay? Now, guys and gals, this is the first time I've ever mentioned this, but integers are whole numbers. They can be positive or negative. You've used them a bunch, and you know this. However, there's actually two types of integers. There is an unsigned, and there is a signed. And the only difference between the two is an unsigned can only be positive. So think about this. The sign on the front tells you if it's a negative or a positive number, doesn't it? So if it's unsigned, in other words, it doesn't have a sign, it can only be positive. But if we have a signed integer, it can be negative and positive. I'm going to show you how that works in a second. I'm going to show you how positive and negative numbers work. Let's just write a quick sentence about our friendly integers and their two new types. And I'm going to show you that there is another problem with integers. Beyond the fact that they're fractional and non-fractional. Yes?
What did you do last week? Because I thought you were doing this, so I've already looked through this whole thing.
So last week we spent most of the time, I think I threw some extra questions in the accepted at the time, and then we did the quiz and the exercise. Yep. So if you just want to jump straight to the quiz and exercise for this one, you've already done this, that's fine. Or is that what you've done?
I did like half the exercise and I did the quiz, yeah.
Oh, okay, cool.
Just what I
Finish
thought-
off the exercise.
That's what I thought you did last week.
Yep. No, we didn't quite get there. But thank you for catching up on that, Tony. That's awesome. All right. Okay, guys. Can I get you to write a little heading underneath, unsigned integers, and write these three questions, and then calculate the decimal value for me, please? Just like we did last week. I'm not throwing anything new into the mix yet.
So is this, for example, if the first 6 120?
If it's a 1. So, before you get to that, Ben, let's do this together. I think it'll make a lot more sense if I just start here.
Okay.
So just write down these questions, calculate them for me. So don't forget your little lovely powers of 2. 1, 2, 4, 8. Try and do it without the calculator if you can. Awesome. Seeing numbers all over the page now, I love doing that. Go. Okay, 1, 2, 4, 8, 16, 32, 128, friends of 10. So that's 160, 176. Power of 10. 128 plus 1 and 2, which is 131. Okay. We've got our good old unsigned integers. If you don't know how to convert, that's something I want you to practice. Go back to the last lesson. But I told you unsigned integers could only be positive, didn't I? That is all we've converted so far is unsigned integers. Here we go. A signed integer. Okay, we are going to do the exact same questions again. But this time, they're going to be signed integers. Guys, are you with me? I hope so. Okay, so have a look at this. Let's write them out again. 1, 2, 3, 1, 2, 1, 1 equals 1, 2, 3, 4, 1, 2, 3, 4. Okay, now, if you ever get a question in an exam, the marker or the question director or the person who made the question will tell you if it's an unsigned or a signed integer. Okay? If they tell you it's a signed integer, what you're going to do is the exact same process we just did with one difference. And that's because we now need to represent positive or negative, don't we? Our good old friend plus and minus. So what we do, everybody, is we take this bit on the front, and this now represents our sign. If that sign bit is a 0, you have a positive number. If that sign bit is a 1, you've got a negative number. So for these three numbers here, what are they? They are all negative. So a plus is a 0 and a minus is a 1. The way I like to think about it is like the absence of a negative, 0. Presence of a negative is a 1. If that helps, whatever. So what we're going to do now, we're going to do the same thing we did before. We'll do our 1, 2, 4, 8, 16, 32, 64, negative 128. Okay? Have a go at this for me, guys. Do the exact same numbers, except for your sign bit is negative. So that literally means negative 128 plus 32 plus 16. Let me know if that doesn't make sense. So again, this is only if you are told it's a signed integer. That very left-hand bit becomes a negative value. Val?
For larger numbers, would it continue to be negative?
The very left-hand one, yes. Yep.
Oh, very left-handed.
It has to be the most significant bit, which is the very far left-hand bit.
Ja.
Yep.
And that works because every number before can add up to one number away from that here.
Absolutely, bingo. Okay, so if we add these two together, we get 48. And if you add it back onto that, we get negative 80. Is that correct? Yep. Thank you. I really appreciate it. 1, 2, negative 128. Add those all together. Well, that only takes away 3, so it should be negative 125. And this one, I'm going to let you guys figure it out, because I'm mean. Ooh. You've already figured it out? Love it.
He is cooking. Is he? He is cooking. So why is that? You'll let us figure that one out.
What is it? What is it? Bingo. Okay. Negative. Now, I've got a quick thing for you. Another limitation about integers. Okay? When I wrote all these ones out here for year 11, most of you calculated 255, yeah? Can I go any higher than that with the same amount of bits? No. That's it. It maxes out. That's the biggest number. If I had an integer like that in Python and I tried to store the number 300 in there, Python would just shit the bed and go, nah, you're done. It's called an overflow because I tried to use more bits that I'm given. However, in Python, we're not given just 1 byte for our integers. We're given 4. So that means the maximum number in Python is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Does anyone want to calculate that for me?
Oh, it's like 2.1 billion something and 2.1.
All right, can I show you a trick? Oh, here we go. Here we go.
34.
All right, what do you got?
4 billion.
Minus 1.
294 million.
No,
Oh,
I think
I
I
went
missed
too
one.
high.
No, we're good.
Surely.
It's
No, it looks right.
264, yeah. And,
All right, there you go. There's your biggest number, everybody. If you try to put a number bigger than that in Python, it will break.
that's unsigned.
Nice. Okay. This is if it's unsigned. All right. So, boys and girls, integers max out. Okay, there is a physical maximum, and let's just pretend for this moment this is an unsigned integer because I used every single one as a number. That means 4.2 billion is the biggest number that I could represent in Python. If it was a signed integer, that value gets halved, essentially, to about 2.14 billion. Okay? Positive and negative. So, do you need to remember this number off by heart? No. Do you need to know that integers max out? Yes. That's the only thing I want you to take away from this, is that integers have a maximum value. Everyone cool with that?
Can you change that maximum value, or is it just set?
If you use different types of integers, yes. So you can import libraries that will give you bigger integers that use 8 bytes. I wouldn't recommend it. Now, guys and gals, obviously, when we're using integers, like if I need to remember Adrian's age, you're doing really well for yourself, Adrian, if you get to that age. Okay. If I need to measure the height of a person, again, holy dooly, integers are going to handle it. But what if I need to measure the distance between here and Pluto? In meters.
In meters.
What's the distance from here to Pluto? Let's see how quick people can Google.
5.1 kilometers.
Oh, I'm glad I choose. 5.1 billion kilometers. So if you tried to store the distance from here to Pluto, even in kilometers, it would crash. It would run out of space. So, boys and girls, going back to here, we've talked about integers, we talked about our 2's complement. I want to talk about this guy, which we've mentioned a lot, floating point numbers. Can I get you all to write something down for me, everybody? Write the heading floating point numbers, and under that in brackets, you with me guys? Put IEEE 754. IEEE 754. You might be thinking that's just the most random garbage you've ever seen in your life. And it sort of is. IEEE is the company that hand out patents to computing science concepts. So when somebody comes up with a standard for integers, IEEE give out the patent. When somebody comes up with a standard for floating point numbers, IEEE give out the patent. When somebody comes up with a standard for Wi-Fi, also known as IEEE 802.11, they give out a patent. Okay? And floating point numbers, why am I telling you this? Because I've actually seen the most arseholist question in my life in the HSC, whereas instead of saying floating point numbers, they said convert the following to an IEEE 754. I thought, you a-holes, all you had to say is floating point number. But they didn't. Okay, you guys thankfully do not need to know how to convert a number into floating point or vice versa. You only need to know about them. Okay, so if you want a fractional number, use a floating point number. Single floating point numbers use 32 bits, also known as 4 bytes, for its data. And its features include, have a look at this number down here. It is redonkulous. It can go from negative 3.1 times 10 to the power of 38. So that is 3.4 with 37 zeros. Or sorry, not even a point. So it'd be 3, 4, and 37 zeros after it. That's a pretty big number, eh? It's past the trillions. You've gone way past that. And then 1.1 times 10 to the power of negative 38, that is 0.36 zeros, 118. Such a small number. It goes from such a stupidly small number to such a huge number. It's absolutely ridiculous. That should have plus minus on the front. The copy paste didn't work. But yeah. The other thing that floating point numbers are really good at, they can represent infinite and NAN, also called natural number. So infinite just basically is like a toggle. If I put in a stupidly big number and floating point numbers can't handle it, it just goes infinite rather than crashing. The other thing is if I try to say my floating point number equals dog, it just goes nan. or not a number. Simple as that. Sounds pretty good, hey? Gigantic ass numbers, really tiny fractional numbers, and you can represent infinite and not a number. That's bloody awesome. But one of the biggest drawbacks, guys and gals, you can't represent 0.01. It's a weird one, isn't it? So floating points, the way they work, and we'll probably get there in year 12, I reckon, they have what's called a range of error. They are imprecise with certain values. And one of those values is 0.01. Or 0.02 is another one. It just kills floating point numbers with the way they work. Now guys, before you keep writing, can I show you a bit of code that I wrote? Okay. Let me just delete that line of code for a second. Here's my lovely program. X equals 0.01. Print X. What do you think is going to appear on the screen when I press play?
Oh, cool. 0.01.
Yeah, cool. So I'll press play.
No, it'll explode.
0.01. Hooray! However, Python is being nice, as Python does. If I tell Python, no, give me all the fractions, I can do what's called a format and tell it to print 30 decimal places instead of just the 2. And then, whoopsie doodle, we'll come back to that one. Look at this. Can you see that weird little number at the bottom there? That's the range of error, the imprecision that it has. It's just got this little extra value that just gets added on to certain values.
Does that change every time?
No. It'll be the exact same imprecision every single time. So because of this, we can't use floating point numbers for things like scientific research, because even that tiny little imprecision can cause massive calculation errors in the long run. So we actually have to use different data types on top of that, which I won't get into today. But yeah. So that's one of the issues we have with floats, is that they are imprecise with very small fractional values. Okay, I'll give you a sec to write anything you need, guys. We've only got a couple more data types to talk about. Year 11, let's do it. Let's do the last one together. Last one, date and time. It does what it says on the tin. It remembers a day, or dates, and it remembers a time. Okay? The way it actually does this is slightly interesting. What they do is they don't remember the day and the month and the year and the hour and the minute and the second separately. What they actually do is they remember how many ticks have passed since the epoch. And the epoch in Python is midnight, 1st of January 1970. Why? Because they can. No?
So is the fact that it counts the ticks why Y2K was theorized to happen?
So the reason Y2K was theorized, it wasn't because of this system. It was because they used to remember dates with only 2 digits. So like 1990 was just 90. And 1978 would have just been 78.
Oh, okay, so 99 was theoretically.
So, yeah, so when we ticked over to 00, how would computers be able to differentiate between the year 2000 or the year 1900 or 1800?
And it just did.
Well, no, there was a lot of work put in.
Okay.
Like 2-3 years before that ever happened, computer scientists were fixing the problem way up until this. And this is one of the solutions, is remembering the ticks since the epoch rather than trying to remember those values individually. Okay? But the really good thing about date and time, guys and gals, is you don't have to worry about all that crap, how it works under the hood. You just have to know that when I store William's birthday, that when I do print date, what's your birthday, Will? 12th of the 8th. You had a year, didn't you? That's what it would tell me. That's all it would say. And it's awesome. As a programmer, I don't have to worry about all the nitty gritty. I just get the date. And I can go, oh, it's almost his birthday, better buy him a present. Okay? The other thing I can do as well is say, all right, how many days are there between Adrian and William's birthday? Okay? And I can literally go, all right, here's Adrian's birthday, here's Will's, subtract them, and it will tell me how many days difference there are between them. So it's a really cool setup as such. You and your hours, boys. All right, boys and girls. Can you all take those lovely writing utensils that you have, put them on the desk. Do not peg them at me. I prefer that not to happen anymore. Everybody, can you go and open up Visual Studio? Make me a brand new file. You might have to open up your folder, by the way, like a new folder or something, since you've been working on your projects. I'm just going to use my Python, and I'm going to call this one. Oh my god, there's so much crap in here. What are you calling it? Let's just call this lists. Okay. So boys and girls, I've just created a new Python file. I've just called it lists. Let's type up a little bit of code. You can change the values if you feel like it. Who's around me? Yeah, we'll just make it a list for now. Just something like that. Actually, I'll get rid of that for the moment. Okay. Take my typing into account, but I've got a bunch of names here. I've got Dingle, Hayden, Adrian, Will, Jensen, and Ben. It's an honour to be on my list here, guys. And then I've got print, then 0 in brackets. Who can tell me when I press play what is going to appear on the screen? Ben?
Dingle.
It's going to say Dingle. All right, I've got a few questions about that one. Why? Ben?
Because it's the first thing on the list.
So why didn't it say,
It's the first.
why didn't I use 1? Hold on, I should fix that, shouldn't I?
Because in Python or in coding, it
Yep.
starts from 0 instead of 1. Because we're on a 10-digit system and 10 is fictitious.
I like it, yeah.
I
Okay,
think so.
so year 11, if I start doing this, guys, by the way, guys, all this is recorded on my mic. So, if I put 0 and then I put 1, what is going to be printed because of this line? Hayden. Hayden is going to be printed. What if I put this one? Jensen will be printed. What if I put this? Alright, so. Oh, I love hitting my power button. So year 11. Are you with me, guys and gals? If I hit play at this point, it's going to print 3 things. It's going to print the first element of my list, print the second element, and then print the 5th element of my list. So 0, 1, 2, 3, 4. Absolutely spot on to those people who said Jensen. There they are. Now, if I try and print something that doesn't exist, let's say I print element number 7, and I hit play, it literally will crash, and it tells me list index is out of range. Just saying purely that this item right here does not exist in the list because there's not enough in the list for it to work. Okay. Now, can anyone tell me what this would print? Why are you saying 6? Okay, what does len stand for? Length. Absolutely spot on. So guys and gals, len is probably one of the most powerful things that you'll come across when you're using lists. If you need to know how many things are in my list, you use the len function. Okay, and you can use len on strings and all sorts of other things. Alright, so quickly write that up. Give yourself a quick example. If you are up for it, chuck a for loop in there to print all the elements. If you remember how to do that. If you don't, that's fine. But is a simple list also known as an array? Okay, all it is the same values being put together one after the other. I want every one of you to hit Control N right now. We're going to make a new script. And I'm going to save this one. And this one's going to be called stacks.py. As in like stacks of pancakes. S-T-A-C-K-S. Okay. Now a list is not a data type. It is what you call a data structure. It's a way of taking primitive data and making it more complex. So what is Dingle on about? Well, I just took a string and made it more complex, didn't I? Now I have more strings. A stack is similar. However, it is what you call a first in. Oh my God, go away you. First in, last out list. So what I'm talking about here, I want you guys to imagine, you know how sometimes you go to a restaurant and they have those like stacks of plates on springs? Anyone ever seen those?
No.
Let's just imagine the plates inside your cupboard there. Alright, Marley's banging for a snack this afternoon. What are you going to eat this afternoon?
Let's go with some good old boys.
Okay, so we're going to get a bowl, aren't we? We're going to plate this down. So, guys, Marley goes into the cupboard, cracks open the cupboard. He goes for the bowls. What's the bowl he's going to grab? He's going to grab the top one, isn't it?
Favorite one.
His favourite bowl. It's like his Paw Patrol favourite one. It's got chase on it, it's blue. Exactly. But he's going to get the top one because that's the logical thing to do. He walks away, then Harry's at Marley's place and goes, I could go for some noodles as well. And he goes and gets the next bowl that's on top. And they go and make them. So boys and girls, this is how stacks work. And it's a bit strange. But the idea is, as we start adding values into our list, the first one actually goes to the bottom. Like the stack of plates or the stack of bowls. The first item goes at the bottom, then the next one goes on top, then on top. And they stack up. So when I want to get to my list, I actually have to get the last one first. Does that make some sense so far? All right, so let's add some things to a list. Let's do the names again. Let's do names. But instead of equals square brackets, I'm going to go empty, like that. And now let's add the names in one by one. Names.append. Dingle. Now I've forgotten which names I had. Hayden. Was it Will? No, Adrian was next. Then Will. Jensen. And who was my lucky last? Ben. Okay. So guys and gals, have a look at that code quickly. What I've done now is I have started my stack of plates. I've put in Dingle, Hayden, Adrian, Will, Jensen, Ben. Taryn, what would be the item on the bottom of my stack?
Dingle.
Why?
Put it in first.
Because I put it in first. Absolutely spot on. So if I was to grab something off this stack of plates, Brody, what would be the first value that would come out? Spot on. Val, shh. Quiet down. So guys and gals, let's try this. The way you access a value in a stack is you do what's called a pop. Okay? Don't ask me why it's called pop. The old terminology used to be push and... Oh, actually. No, they don't have it. Never mind that one. So it used to be called a push and a pop, but we call it append and pop. So what I'm going to do is I'm going to put print names pop. And if I run this code, what do you think is going to appear on the screen, Tommy? So have a look at my stack. Access, yep, spot on. Press play, out comes Ben. Now guys and gals, the important thing to note about stacks is when you pop a value, it actually is gone. So when I pop and I get Ben, his name actually disappears off the list. So, yes, Tony.
If you print names that pop after that, it'll demonstrate that it's under Jensen.
Excellent. So if I pop twice, you'll see it goes Ben, then Jensen. I'm slowly removing you people. Have a go. Have a play around. Get a few minutes on this one. So year 11. You might be thinking, what the hell is the point of this? Why do I want to stack? And then every time I try and access a value, it gets removed from the list. It's actually incredibly handy. Hands up if you played Tetris before. Or even watched a Tetris game. Excellent. So you all know what I'm talking about roughly. The way Tetris works is you have 6 main blocks, yeah? You've got the L's, you've got the Z's, you've got the line, and you've got the square. Not their real names. Oh, no, 7, because there's also the T piece. All right? What happens is when you start the game actually shuffles all 7 pieces together in a bag. It's called a bag shuffle. and it puts them in a stack. So it goes T-piece, L-piece, square piece, all the other bits. And then what it does is the first piece you get comes off the stack. And then the next one comes off the stack. And the next one comes off the stack. And when it runs out, shuffles them again. Another example, hands up if you've played Pokemon before. Any of the Pokemon series. Excellent. Most people. One of the most prevalent things in Pokemon is the Pokemon speed. Why is the Pokemon speed important, Marlon?
Oh, the Pokemon speed.
Yeah, why is it
When you're in a
important?
battle.
Yeah.
Well, when you're throwing the ball.
No, just like you're fighting.
Oh, maybe because it's a turn-based game. Maybe because it's so quick that maybe you need like one turn, like one input, and then it attacks you.
Ooh, I like your thoughts. Not quite what I'm going for.
So, Pokemons have speed, and whichever one has the highest speed stat goes first.
Exactly right.
Oh.
Except for some moves, such as quick attack.
We'll get to that in a second. So quite literally, guys and gals, what happens in Pokemon? Thanks, boys. What happens in Pokemon is you actually make all your moves, especially when you've got 4 Pokemon on the battlefield. You choose your 4 moves, and then the game goes, all right, who's attacking last? And they get added to the stack first. Who's attacking next? They would get added, and then the fastest would go on the bottom because when we access the first attack, that comes out first. It's the fastest attack. Sorry, Marley.
Wait, so it's not based on your inputs. It just takes the quickest one?
Yeah, it does. Yep.
What did you think?
That's how Pokemon works. It's the quickest goes first.
Pokemon, mate.
All right.
I think the most I played was a DS game that barely ran.
Guys and gals, have we got any more questions about this one? Stacks are fairly straightforward. It's like a list, but you have to access it from the back to the front. All right, new list. We're going to call this 2D lists dot py. 2D lists dot py. Okay. All right. So we have a list. Okay. I'm going to go to my good old friend Excel for a second, and you guys are going to point your eyeballs up here for me. Oh my God, that's bright. All right. I'm going to put Dingle, Marley, Harry. Oh. Tell you what, I'll take myself off. How's that sound? How's that sound? Zach can go in my place. Dobby can go in there as well. Val, because he keeps swinging around. All right, Zach. Give me a number, 1 to 100.
He's doing this.
64.
64. Another one.
32.
32. Another one.
18.
18. Excellent. Marley.
98. 99. 100.
Excellent. Harry.
I'm going to go with a 3. I'm going to go with a 2. Maybe a 5.
Oh, nailed it. Dobby. 50. Right down the centre, yep.
64. Oh, wait,
I don't care.
72.
And 72. And Val.
252.
So 5. Yep, sure.
Maybe
A
a 21.
21, yep.
Maybe. Can I go 0?
You can, okay, I'll give you a 0. How's that sound? Okay, excellent. Everybody, I'm going to skip back to our other example. What were my names again? Dingle, Hayden. I've already forgotten Adrian. You were next, weren't you? Will, Jensen, and Ben. Guys and gals, if you were to picture a list, this would be a list. All right? So what we did before, we added all those values into our names list. There's me in position 0, there's Hayden in position 1, there's Adrian in position 2. That is called a one-dimensional array. So when we access the value, we only go with a single number, don't we? So when I printed Adrian's name, I said print names 2, and Adrian would come. That's what you call a single dimension. However, what if we want 2 dimensions? I want X and Y. Well, that's when this comes in. You can actually have multi-dimensional lists or arrays in Python, and this is where things get a little complicated, but stay with me. What it essentially means is I now have access to an X value going across, and I have a Y value going down. So if I want to access, let's say, Dobby's first assessment results, I would go across to this column and down to this row. And I'd find out that Dobby got 50 for his first assessment. Indeed. I mean, Harry nailed it. So if I wanted Harry's last assessment, I'd go across to D, and down to 3. Does that make some sense so far, everybody? Because what we're about to do will be very confusing without this. So, what I'm going to do, guys, I'm going to push this to one side, and I'll write my code on the left, and hopefully it'll make a bit more sense. Surprisingly not. Okay, so everybody, I'm going to put student marks equals square brackets to make a list. Stay with me, guys, don't rush ahead. And to add in Zach's results, what I would do is go student marks dot append, just like we did with the with the stack. And in the brackets, this is the only confusing bit in my opinion, I put another square brackets. I'm adding a list to my existing list. And in the brackets, I will put Zach, put a comma, 64, put a comma, 32, put a comma, 18. Okay. There we go, that's a bit better. Is everyone okay with that, somewhat? And then we're going to do it again. Let's add in Marley. He got a 98.
Well, I wish that was actual.
You will, mate. 100%. And Harry didn't get enough sleep the night before. And Val did incredible with the 0. Let's print. Alright, year 11. Come with me, guys. So, if I would like to print something, just like we did before with the names, I just put square brackets and then provide the index. So in this case, I'd like to check out Harry's good work. So I would type in 0, 1, 2 for Harry. Okay, if I press play, you'll notice that it just spews everything about Harry in one go, which is good, because that's what I wanted to start with. But let's say I want to boil it down to Harry's first mark. What you've got to think about then is we have a list inside a list, a 2D list. So I'm accessing Harry's list, and if I want to access this value here, I put a second set of square brackets, and then the index for the value in Harry. So Harry be 0, 3 would be 1. So if I press play, you'll see it just prints 3 down the bottom. So it's a little bit weird, but think of it like X and Y values. Okay? So if let's say I do 4, who can tell me what's going to be printed on the screen there? Bingo, Val's 0. Absolutely spot on. Because it'll be the 5th list, or the 4th spot, so 1, 2, 3, 4 is the 0. Right at the end. This is a 2-dimensional list. Now, if you've played any video game in your entire life, you have encountered a 2D list.
I'm trying to think.
Yeah?
Yeah.
X and Y coordinates, just moving around a game. If you've ever done like a top-down game, again, Pokemon. X and Y, your character moves around in blocks, don't they? Because it's all 2D array. They would say, this square is grass, this square is a house, this square is a Pokemon. And as you walk around the world, if you run into one of those tiles, it goes, oh, you're in a fight. Off you go. Okay, so 2D arrays are really goddamn common in this world. All right, guys and gals, I'm actually going to pause here. We've got 20 minutes until the bell. And I'm going to ask you to jump into exercise 1.5. 5. The quiz. And have a go at the exercise if you get time. We've still got one more thing we need to talk about, but I'm going to save that for Thursday.
So you want to see my name?